Okay, so good afternoon and welcome to this session. In this session, we will be solving a uniqueness of Cauchy problem. Okay, earlier we have seen how to solve a Cauchy problem previously. If you have seen my videos, then that's fine. If you have not, you can watch the videos in the playlist and then get back to the same video again. We have learned to solve a partial differential equation by using, in fact, Lagrange multipliers, and then we solve for Cauchy problems. And now we will be proceeding whether we will get a particular solution, a unique solution, or no solution, infinite solution. So such kind of things are studied in the uniqueness of Cauchy problem, right? So you may consider a differential equation, partial. So consider a partial differential equation. So consider a partial differential equation of, let's say, p x y z, a function of x y z with del z over del x plus q of x y z, then del z over del y equal to r of x, y, and z, right? Now you will be given an initial curve. So let me write down the initial curve. So with the initial curve, say gamma, and it goes from x naught of t, and then y naught of t, and z naught of t. It can be a function of t or function of s as well. All right. So here we will see. So you just have to see the case one. Case one is when, under what conditions you will have a unique solution. Okay, so I just want to study when this system will have a unique solution. So unique solution only when you get this is p of x naught, y naught, z naught upon dx naught of dt is not equal to q of x naught, y naught, z naught upon dy naught upon dt. When these two ratios are not equal, in that case we will get a unique solution. Or one can even consider, or you can even consider this determinant. Okay, consider a determinant of p x naught, y naught, and z naught. See, when I'm writing x naught, y naught, z naught, that I'm talking about these curves. Okay, and say q of x naught, y naught, z naught, and then consider the same thing, dx naught over dt, and then dy naught over dt. All right, if this determinant is not equal to 0, in that case we will get a unique solution. Now comes case 2. Case 2 is for no solution. Suppose it happened that you found these two determinants equal. These two ratios equal. Okay, so p of x naught, y naught, z naught upon dx naught on dt equals q of x naught, y naught, z naught upon dy naught upon dt. Just a moment. Yeah, welcome back. So q of x naught, y naught, z naught upon dy naught over dt, and this thing is, these two are equal, but it is not equal to r of x naught, y naught, z naught on dz naught over dt. Okay, in that case you will get no solution. Now comes another case 3, where you get infinite solutions. So one thing is sure, when it was not equal, you got unique. When these two are equal but not equal to the third one, you got no solution. And when all of them are equal, you get infinite solutions. When all of them are equal, you get an infinite solution. So dx naught over del t, this will be equal to some q of x naught, y naught, z naught on dy naught over dt, and this will be equal to r of x naught, y naught, z naught upon dz naught over del t. In that case, we will get infinite solutions. So this is quite easy thing, and mostly and most often it's asked in a GATE as well as in CSIR net. Okay, so just look at the problem very carefully. You have to understand when this PD has unique solution or no solution or infinite solution. You can simply, without solving the problem, you just consider these three equations and solve them to predict not in fact to say that equation will have a unique solution or an infinite solution or no solution. So we will now consider a problem to understand. Let's take an example. One, let's say you got a Cauchy problem. So consider a Cauchy problem. So consider a Cauchy problem. So you got ux minus uy equals 2. Okay. With the initial curve, say 2s comma s comma 2s. Okay. So whenever you get such kind of problem, you just have to check what is p of xyz. P of xyz here is 1 and q of xyz is minus 1. R of xyz is 2 on the right hand side, and this is your gamma, and here you have 2s comma s comma 2s. So that is x naught of s is your 2s, y naught of s is your s, and then z naught of s is your 2s. Now consider the ratio. Let's consider p of x naught, y naught, z naught on dx naught over ds. So what is that? P of x naught, y naught. Anything you put here, you just get 1. Now if you differentiate dx naught over ds, you get 2. Okay. And let's consider q x naught, y naught, z naught on dy naught on ds. You got q of x naught, y naught, z naught is minus 1. And if you differentiate, you get here 1. So these two ratios are not equal. So therefore, p of x naught, y naught, z naught upon dx naught upon ds is not equal to q of x naught, y naught, z naught upon dy naught upon ds. So in this case, we will have a unique solution. Okay, so this has unique solution. And if you want to see how that unique solution looks like, wait, let me solve in fact. So let's find out what that unique solution is. So by Lagrange method. So by Lagrange method, you can simply get that unique solution. So dx over p equals dy over q equals dz over r. So dx upon p is 1 equal to dy q is minus 1 and dz over r is 2. So you simply solve first two pair. So you get x equal to minus y plus c1. So from here you get x plus y equal to c1. And now consider any two pair. So I consider last two. So I get minus y equal to 1 upon 2 z plus c2. Just take this here. So you get minus 2y minus z equal to c2. I'll simply multiply by minus. So it will be 2y plus z equal to, I'll call it another constant, say c3. Okay. So I'm getting phi of c1 equal to c3, or you can say phi of c3 equal to c1. So this implies you have phi of x plus y equals 2y plus z. Now consider the curve you are given, that is your 2s comma s comma 2s. Now consider, so therefore phi of x is 2s and plus y is again s. This will be equal to 2 times y is s and plus z is 2s. So you get phi of 3s equal to, this is 4 by 3. So this will be 4s, and now put 3s equal to some w and see what you get. S equal to w by 3. So therefore phi of w will be equal to 4 and s is w by 3. So I got this. So if I want to remove this phi, so I have to take phi of x plus y. So if I take phi of x plus y, I'll be getting x plus y equals to 4 upon 3 times x plus y. But I know that deep down phi of x plus y I'm given to be 2y plus z. This is what I have found. So now these two are equal. So my unknown function phi is removed, and I got a unique solution. Nice one. That looks like this. All right, so that looks like this. And now you can consider solving it more further. And in that case, you get simply 4 by 3 times x plus y, 2y plus z. Now just multiply 3 here, so you get 6y plus z equal to 4x plus 4y. Now you get z, keep the z here, you just take that one there. So you get 4x minus 2y. Okay. Now you may argue that, sir, you have taken first two pairs and the second two pairs, so you got a solution. What if I take first and third? Okay. In the case you are doubtful in that case, so I'll say you can consider first and third pair, first and third pair, and arrive at the same result, I bet. Okay, because we have predicted that it will have a unique solution, so you can't expect any other solution. Okay, you can try and see. I have tried and I've solved. Now let's go further. Let's have a let's solve problem number 2. So I have another problem here ready, and it says you have ux minus uy equal to, and please just one request here. I'm writing everywhere z, and the problem is given in u, so you may not wonder, okay, why am I doing all these things? Because in the case you are worrying, so you can simply take, instead of u, you can write down z. Okay, because u creates a confusion, so that's why I write every time z. Zx simply means partial derivative of z with respect to x. That is what I mean. Okay, generally it's a standard practice to write u and then solution is given by u equals to, but I don't like. Okay, so here also I'll just change the notation. Instead of u, I'll write down z. Okay, so here you have a big z. Zy equals to z. It passes through s comma sin s, then number of solutions of this PDE, the number of solutions of this PDE are. So your options are unique, exactly 2, C, no solution, and D, infinite. So in that case, you just have to solve. You are not required to solve this entire PD by using Lagrange method. I just solve just for a verification, so that you understand that even after solving the big Lagrange equation, you are going to get the same solution which you predicted. If someone is asking like what kind of solution this PD will have, so you just have to tell them whether it will have unique solution, no solution, or infinite solution. Okay, so that much you have to do. So you may consider now. I'll be taking another problem. So meanwhile, just hold a moment. There's some connectivity issue here. So recording needs to be paused. Hold a moment. Oh yes, so I'm back. Now, so you just have to first take into the consideration what is your p of x, y, z. So here you have got lucky you are 1 and it is -1. So I'm done with this. And then q of x, y, z will be -1, and r of x, y, z will be equal to your simply z. Now watch out. And gamma is the curve given, and it is your s, and then sin s. So you can say x naught of s is just s, and y naught of s is again s, and z naught of s is sin s. Now we will consider. So consider, find out the ratio each first, and then let's see what will happen. So p of x naught, y naught, z naught upon dx naught over dx. So p of x naught y naught, it is 1, so no matter what you put, you are going to get 1 only. Now differentiate this with respect to x, so you get 1. Okay, and it gives you 1. Now consider this one. So q of x naught y naught z naught upon dy naught upon ds. Q of x naught y naught, it is again minus 1. So you got here minus 1. And then the derivative of this will be again 1. So you got here minus 1. These two ratios again are not equal. So in that case, you will have a unique solution. Okay, so you can say that since p of x naught y naught z naught upon dx naught upon ds is not equal to q of x naught y naught z naught on dy naught over ds. So this implies this PD as a unique solution. Okay, this PD will have a unique solution. Now example 3. So ux ui equal to u, and you are given u of s comma s equal to sin s. Then number of solutions of this PDE. You can try it first, and then let me recall it. In fact, for the time you can just try and see what you get. So I hope you got the solution, right? If you tried. So here I'll explain. You got here p x y naught. Here I'm taking, it's no more now, it's there, it's u, so I'm taking u just to give you a thorough practice. So x y u will be just 1, and here q is again 1, and u here r of x y u is u. Okay, so now you got your initial curve, that is s s, and then this is u. When I say z of x y equal to something, or you say u of x y equal to something, that means u is a function of x and y, so final result will be simply u. So I can remove down this u and say this is my u thing. Okay, so now u of s comma s is sin s, that means this is x, this is y, and this is u. So I got s s and sin s. So x naught of s is s, and y naught of s is again s, z, and u naught of s is sin s. So consider this ratio, and you got here 1, and then derivative of x naught will be simply 1. Again, same thing here, 1 and 1. Here, now it is u. R of x y naught is u, but you want what? R of x naught y naught u naught. But u naught I have got to be sin s. So it will be simply replaced by sin s, and then derivative will be cos s. Now, the first two are equal but not equal to the third one. So this PD has no solution. In case you wonder why it has no solution, so you can simply solve this by Lagrange method and see what will happen. Okay, so in case you are wondering, so really? So let me consider the Lagrange equation. So you get dx over 1 and then dy over 1 equal to, and please do allow me to write down z. I think that it is u. Okay, think that it is u. No issues. Okay, because I have no practice of writing this u. Every time I write even z. So consider the first two pairs. So you get x equal to y plus c. So from here you get x minus y equal to c1. So the first thing, and now you consider first or the second pair, no one cares. So I'll consider first and third, okay, for your simplicity. So x will be equal to log z and plus c2, right? I'm integrating, considering first this pair and simply integrating. So dx integration will be x, and d by z, dz upon z will be log z plus c2. So from here I get x minus log z equal to c2. Okay. Now you may consider this. So phi of c2 equal to c1, or you say phi of c1 equal to c2. But I'll advise you to take phi of c2, or you can take any, no problem, because if you take this phi of c1, okay, just let me show you here. You should not think anything. So x minus y, and then just a moment, phi of c2. C2 is what? This is equal to x minus log z, and here I'll be getting x minus log z equal to x minus y. Now I have the curve. What is that? It is simply s, s, and then sin s. Here also I have s, s, and sin s. I'm just trying to explain that why you get no solution. Okay, you've said you got no solution. So is it really without solving? If you predicted, Okay, what if you solve? So phi of x is s minus log of sin s equal to, see here, s minus s will be 0. And here if you do, you get the same thing, s minus s will be 0. You are saying phi of 0 as something, s minus log of sin s. These two things are quite contradictory. Okay, but even if you do it, no issues. Phi of s minus log x, anything will be 0. So that means if I replace x minus log z, I'll be again getting 0. So this implies what? X minus y will be 0. So this implies x equal to y. And here if you do, then phi of 0, you are saying s minus log s. Now here I can't conclude anything. Okay, from here this condition is really absurd, because when you are putting something 0, you are getting as a function. So this is not possible. And from here you got x equal to y, and this is not a solution, by the way. Where is it? Where is u? There is no u, so this is not a solution. In fact, whatever you have obtained will not satisfy your equation. So this equation basically has got no solution, and we fixed it, right? So stay tuned, and we will meet in lecture 6 with Sharpie method of complete integral, and there we are going to solve basically a non-homogeneous part, okay, and non-linear integrals, non-linear PD, in fact. Okay, so thanks for watching.